So this is work done in healthy older adults, but will potentially and hopefully will give us insights also in patients with dementia. And this is some work that we've been collaborating with the James Rose group with frontotemporal dementia. So since this is quite an unusual structure and people might not know, I will give a brief background on what's the locus coeruleus, where it's located, and what is it used for in humans. And then I'll give a bit of a background literature on how it's been imaged over the past years. And then I'll go onto the actual study that we've been acquiring on the 70, in which we have actually decided to acquire multiple types of techniques on the 70 to image the LC, both structurally and functionally, in functional images in healthy older adults. And finally, some conclusions. So the locus coeruleus is a very, very tiny structure. It has about 2 millimeters, is about 2 millimeters wide and 15 millimeter long, and is located in here, at the base of the fourth ventricle. It has many projections throughout the central nervous system, and is implicated in specific cognitive functions such as attention, memory, cognitive control, arousal, etc. And the LC is known to have neuromodulatory neurons that produce neuromelanin. And this neuromelanin is neuroprotective, has a neuroprotective role, which means that it chelates environmental toxins such as heavy metals, example like free iron or something. So this is very important for diseases such as dementia. And here are some microscopic specimens of the LC in healthy subjects and in a Parkinson's disease subject. And the LC has been stained for neuromelanin. And you can see that in the healthy subject is very clear, those two dots on the side. And in Parkinson's disease subject, it's greatly reduced owing to neuronal depletion. However, imaging is a bit more difficult. And in the past, they have been using sort of T1-weighted fast spin echo sequences. And you can see here that it's quite clear in the healthy subject that you can see these two dots. And in the Parkinson's disease subject, they are slightly diminished. And however, you can see that the resolution is quite high in plane, but the slice thickness is very, very low. So you can't even actually see the whole structure on a 3D projection. And also, in addition to this, the acquisition time for this type of sequences is quite long, is more than 10 minutes. So there has been other studies looking at the locus coeruleus MRI contrast, and this paper actually has looked at this quite deeply and has stated that the contrast on the T1-weighted TSE images are actually a result of resonance magnetization transfer effects. And what this means is that we are actually, the sequence itself is not having a T1 effect, but actually an MT effect. And so we could actually create MT-weighted sequences to excite the neuromelanin, which is a macromolecule of resonance, and actually acquire data in this way. So what is a magnetization transfer effect? So macromolecules like the neuromelanin in the locus coeruleus, even if they are bound to water, have a very, very short T2. And this makes very difficult compared to water, free water that has long T2, that the longitudinal magnetization will decay very fast and will not be able to measure it very well. However, it does have a broad absorption line shape compared to water, and this means that if we can excite them off resonance, they become 10 to the 6 times more sensitive than if they are excited on resonance. So if we are exciting them off resonance, the coupling between the macromolecular protons and the mobile protons or liquid protons allows exchange processes, and these exchange processes are what we call magnetization transfer. So the magnetization transfer process is essentially the longitudinal magnetization of one pole affecting the longitudinal magnetization of the other pole. And so if we excite these macromolecules of resonance with an RF pulse, and we wait a bit, the magnetization of the macromolecular pool will affect the free water. And this is essentially what we do. And then there have been some studies before, and this is quite an interesting one, because they have developed this new sequence, an empty sequence, using a turboflash readout. And there are quite a few advantages on this, because not only you can increase the resolution quite a lot, but you can decrease the acquisition time as well, and you increase the contrast in the LC, as you can see more or less. So we, using this type of method, we implemented the sequence here in Cambridge as well, and we applied a train of 20 RF pulses applied at 6 ppm of resonance before the 3D low flip angle readout. We also acquire a non-empty weighted sequence, which essentially means not having those off-resonance pulses, and the image itself appears sort of like a PD weighted image. So essentially now we have scanned 15 subjects with this type of sequence at 7T, and they're all in the older, around 66 years old. We acquired the MT sequence in 3 repeats. We acquired 3 times, just covering the midbrain area, so the LC and the substantia nigra. And the sequence parameters are very similar to the paper that I cited just before. We also acquired 1 repeat without the MT pulses. We also acquired 3D multi-echo T2 star sequence, and this because it will allow us to calculate QSM and R2 star, and these are measures that are related and directly related to iron depositions in the brain. And since neuromelanin is chelating iron, it is very important for us to also acquire this sort of data. We also acquired resting state fMRI because we wanted to look at the functional connectivity of the locus coeruleus with the whole brain. And so we developed a sequence protocol with 1.1 millimeter isotropic. It's covering the whole brain, and it takes around 10 minutes for connectivity analysis. And also we acquired an MP2 RAGE whole brain at high resolution. So about data analysis for the MT sequences, since we had 3 repeats of each run, for each subject I used ANTS to create an MT combined sequence, and the ANTS will actually improves the registration in between the repeats compared to any other registration methods. And yeah. And then on this MT combined space for each subject, I manually segmented the LC left and right. I segmented a reference region, which is shown in blue, which had about 37 millimeter cube volume. And I also segmented the fourth ventricle for each subject. With these regions, I calculated different types of measurements, sort of like CNR of the locus coeruleus in left and right, the MTR, and also some topological measures such as LC length and diameter. With all the data from all subjects, I applied a 2-step template construction with with ANTS, and which allowed us to create an empty template of all the 15 subjects we had acquired. This is related to the QSM data. For each subject, I calculated QSM and R2 star maps from T2 star data. QSM maps were calculated using Julio's QSM box pipeline. R2 star was simply a voxel-wise exponential fit on the multi-echo data. But essentially, this data was registered then via MP2Rage to the MT combined data for each subject. And in this space, we calculated metrics such as key average and R2 star average in the LC for each subject, using the ROIs from the MT data. We also built QSM and R2 star templates using the fine matrices calculated previously. Yeah. That's it. So here is the results for the MT data. This is MT data template from 15 subjects, and you can see clearly on the top row that the locus coeruleus is very clear, left and right in all of the projections. Also, the segmentation, the subject-wise segmentations were combined, and I combined them and created a probabilistic segmentation average map, and this is shown on the second row, and you can see that is very accurately overlapping the LC. I mapped other probabilistic maps that are atlases that are available, freely available, and this is one example here. This is 3T data, and the data is quite low resolution. So the atlases are much more broader, but they still locate in the same regions, and they are in accordance to our data. This is QSM and R2 star data, subject average in across all 15 subjects. And you can see here that there is no actual contrast in QSM on R2 star within the region of the LC. In red, you can see that there's the MT ROIs are mapped just for convenience, and we did not find any iron type contrast within the locus coeruleus. Here are a table of quantitative measurements. We did find symmetry in topology, both on the left and right LC, so there were no actual differences in the measurements we took. And this is in accordance with Bet's paper in 2017. We used a T1 flash sequence. So this was quite good. On average, even if the CNR and MTR values were quite high, for very small structures, we found that on average the estimated LC size was smaller than previous estimates that were obtained using histology. Also, I would like to point out that, again, that we didn't find any intensity contrast in this older adult group, but we report key and R2 star values for the LC regions, left and right, and we might find that these values will change in other patient groups. In terms of the fMRI analysis, we used a very simple standard pre-processing pipeline, and we decided to take an exploratory approach using a seed to voxel analysis because to start off this type of analysis. So essentially, we used a seed on the left and right LC altogether. We used the manually drawn seeds mapped onto fMRI space, and we included nuisance regresses such as white matter CSF and forced ventricle signals, the principal components of these ROIs as well. We included respiration and cardiac regresses obtained from RetroICOR implementation in PhysIO. And we included 24 motion regressors, so the 6 motion regressors and their derivatives, first derivatives. And here are the results. I suppose you're more familiar with fMRI than I am. Resting state, and you might find that this is very scattered. The voxels or the clusters are very small, and we kind of do expect this to happen because the effect size is really quite small. The LC region is really small at 1 millimeter cube resolution, in which is mapped here in this MNI space. So this approach is all right to start off with, but we do think we need to evolve onto some sort of ROI to ROI analysis for the future. But we do find that the regions that are sort of actively connecting with the seed are regions that are expected. So to conclude, the MT-weighted imaging revealed clear LC contrast for every subject, in which we were able to segment left and right locus coeruleus. And these masks were generated are in good agreement with previous work. The LC size is slightly smaller than previous estimates, but we know that LC is heterogeneous. It not only includes neuromelanin, so MT-weighted images only excite neuromelanin, so this might not show the total LC volume, but it shows only the neuromelanin content on the LC. Potential changes, well, we didn't find any contrast on QSM and R2 star values on healthy cohorts, but we might find potential changes on these values when we analyze data with patient groups. The fMRI connectivity, there was fMRI connectivity in cortical regions and in the cerebellum. However, we do think the effect size is maybe too small. We have a very small group. So further analysis must be done with this data. And if you have any suggestions, I would be very welcome. Thank you very much for hearing me.